So what does supersymmetry mean? Supersymmetry refers to possible relation between the spectrum and interaction of fermion and boson. So you have fermion here in one group and boson in one group. So what is supersymmetry trying to connect these two? And explain these two in terms of supersymmetry. It can be viewed as a space-time extension of the Poincare group. So, supersymmetry. So, since we are dealing with space and time, why this group? Because this group is first, it is Lorentz invariant. It is also translational invariant. Lorentz invariant is important because every existing particle in the universe must obey special relativity. Special relativity lah itu yang memberikan the Lorentz invariant is the key to special relativity. Contohnya, if you travel at higher speed, your half-life is increased. Saya tak pasti dengan kamu saya ajar special relativity tidak, tapi yang tahun lepas saya ajar modern fizik. Seolah-olah arwahnya tahu dia nak pergi dah. Padahal masa itu dia salah seorang yang mengajar modern fizik dengan dua orang lagi, iaitu Kaprasa dengan Datuk Muhammad Yahya. Arwahnya kata, dan kau ambil lah, tak larat nak mengajar modern fizik, saya pun mengajar. Dan saya tekankan di situ ada special relativity, okay, which has Lorentz invariant. Tapi it involves a new anti-commuting dimension. Need to provide what you call anti-commuting dimension. Senang cerita, this supersymmetry will involve higher dimension. Supersymmetry provide a new route to unify gravity with other interaction through superstring theory. It is straightforward to construct a supersymmetric version of the standard model, the MSSM or SU5, and the larger grand unified groups. In each case, each particle of spin 0, half or 1 is accompanied by a predicted superpartner which differ in spin by half unit. In addition to this doubling of the spectrum, one must introduce two Higgs doublet or Higgs boson as well as their spin half superpartner. So because this so basically the idea is you have to you have a boson in the supersymmetry. The boson, say a spin 0, 1. In supersymmetry, any particle is have a super partner. That differ by half speed. Dia punya unit sekali kita tulis half h bar speed values. So similarly, the Higgs particle must also have its super partner. So any particle will have it. So you have a particles here, and here it must have a super partner. This is the idea of supersymmetry. To go deeper into this idea of supersymmetry will be difficult because you need to go into group theory. Of course, the final story about grand unification is via the superstring. And that goes together with higher dimension automatically. When you deal with superstring, you must go to higher dimension. Actually, if you want to know more in detail, there are always a lot of YouTube. Kalau you cari superstring or YouTube in your lectures, you will see some very good superstring lecture and physics in higher dimension. So in general, in this, so I'm not going to talk about superstring because I don't have, but if you like, you can go to the internet. But I can say something about higher dimension. This, what we call additional space dimension, beyond 3, they are thought to be compactified or curled up into tiny circle or other manifold, highly warped by gravitational effect, or because some dynamical principle causes it to be stuck in a limited domain of new dimension. So these are, so one is so-called curl up space dimension. So why are these curl up into tiny circle or manifold? Nobody really knows. Okay, but it could be gravitational effect. Why is it very likely? It could be why gravitational effect? Because gravity theory is space-time theory. Okay, it space and time. So it is possible that space is curled by this gravitational effect. The higher dimension, the 3 dimension is opened up, but the other dimension are curled by this gravitational effect. So gravity is indeed a bit weird. Mengapa dimension lain dia tertutup macam bawang? Kita tengok bawang tu permukaan, tapi dalam bawang tu banyak curl up space. Or some dynamical principle. Yang ni kita tak tahu. Mungkin tanpa curl up space, space time yang kita alami ini maybe not stable. So all these higher dimension are curl up because 3 space and 1 time dimension need to be stabilized. Contoh mungkinlah ini dynamical effect ya, or dynamical principle, we don't know. And then of course and then this grand unification symmetry may be broken by boundary condition in the extra dimension, so that our apparent 4-dimensional world has a lower symmetry. Itu hal ya. So itu sebabnya yang terakhir tadi ialah besarkan lagi apa ni, group 2 yang melibatkan higher dimension. So grand unified theory punya symmetry may be broken by boundary conditions in extra dimension, in high dimension. Jadi dia macam begini, dia adik-beradik juga dengan higher symmetry broken into less complicated or lower symmetry. Okay, this high symmetry, ini lower symmetry. So mungkin this higher dimension pun itu sifatnya high dimension, and then berlakunya broken symmetry or symmetry breaking mechanism, maka our 4-dimensional world or universe so maybe di sini sebetulnya berlaku grand unification ini, tapi yang kita tengok di alam ni yang ini, itu yang mungkin skala-skala ni ataupun coupling-coupling ni tak bertemu. Tapi kalau dilihat di alam dimensi tinggi mungkin dia bertemu. Tapi nak lihat ni macam mana? Itu satu hal juga. Maybe when you go to higher energy, there is possibility that you are opening up this. So maybe to go from here, you need high energy, which will open up so-called curl up space. Okay, terbuka alam lain. That's why kalau kita go to the theory actually, the Large Hadron Collider yang sekarang ni baru hidup balik semula, biasanya benda-benda ni dia balik semula sebab ada pump duit ya. Maknanya duit mencukupi untuk run the Large Hadron Collider. Maka there is possibility kita akan nampak black hole dengan Large Hadron Collider yang akan datang. So this is one of the exciting story. Maybe kalau kamu ada peluang bekerja dengan CERN, then maybe you can look up for black hole. Because these black hole are not ordinary black hole that exist yang kita nampak di galaksi. Yang ini black hole at high dimension. Sebab apa? Curl up. So black hole not just in this 4-dimensional world yang orang kata exist in the center of galaxy. Mengapa dia berputar? Sebab Kaabahnya itulah black hole. Okay? That is the current theory based on simple Einstein equation, which is 4-dimensional. But you go to the higher dimension, there is possibility that Large Hadron Collider boleh nampak black hole ni. So very exciting. Maknanya mungkin boleh mungkin through symmetry breaking mechanism, this black hole in high dimension is equivalent with the black hole yang dilihat di center of galaxy. Mungkin itu pun satu cerita. Now so it is true that the symmetry in our 4D universe are of lower symmetry, higher dimension, higher symmetry. Of course, because lagi banyak dimension, lagi banyak possibility untuk bersimetri. But this is not under well, you can say it is a kind of the symmetry breaking. It is not grand unification, but it is a mechanism, not a mechanism of grand unification. You can say symmetry breaking is important. Why? Because it connects lower symmetry to higher symmetry. And higher symmetry is the unification. So higher symmetry leads to unification. But the present universe might be of lower symmetry. So how you go to higher symmetry? Either you go to higher energy or higher dimension. Itu je. So Higgs symmetry breaking mechanism. The reason is why symmetry breaking ni mechanism ni banyak. But it seems that the Higgs symmetry breaking mechanism is the one that seems to be true, to exist in the universe. Why? Because through this model, the Higgs boson was discovered. So this Higgs mechanism is essential to explain the generation mechanism of the property of mass of all the gauge boson. So this, just before we go to the detail, this is generating mechanism. For mass of gauge boson. This is very interesting. Itu sebabnya Higgs boson penting. Because the interaction between the various gauge boson with the Higgs boson give them the mass. Satu hal juga tu. Apa faham tu? Mungkin kalau nak lebih mudah faham ialah saya takarkan dia punya ni in the standard model. Sebetulnya in the GWS sebetulnya yang ni, tapi never mind. The 3 weak boson gauge boson, that is the W plus, W minus and the Z0, gain mass through the Higgs mechanism by interacting with Higgs field that permeate all space. Dia agak pelik yang ni. Dari segi tu, dari segi konsep dia. Dia macam manusia juga. Katakan Higgs boson ni, apa ni, sorry, this gauge boson ni, W dengan Z ni, tidak mempunyai jisim macam foton, massless. Dia wujud tapi dia tak ada berat. Tiba-tiba dia lalu satu awan. Awan ni adalah awan Higgs lah ni. Dia lalu tiba-tiba dia ada jisim, dia berat. Macam mana? So konsep ni macam kata orang tu macam bergantung sikit lah konsepnya. Maknanya bila kita melalui Higgs field ni, baru kita merasai kewujudan kita ada jisim. Kalau tidak melayang gimana kan, tak tahu olah lah. Tapi bila melalui gelombang ni atau Higgs field, medan Higgs ni, baru tiba-tiba kita rasa kita ada berat, ada jisim. So bosons are generally massless, but the Higgs field induce what we call a spontaneous symmetry breaking. So dalam teori standard model ni, khasnya GWS, the Higgs field, the 3 boson ni exists as a what you call a Nambu-Goldstone boson. Which is massless. Interact with Higgs field baru dia jadi gauge boson. So in the theory, all the 3 weak gauge boson are initially massless. Dipanggil sebagai Nambu-Goldstone boson. Bila berinteraksi dengan medan Higgs baru, tapi medan Higgs itu sendiri terdiri daripada Higgs boson. Terdiri daripada droplet air Higgs ini. Ya tak? Kita kalau melalui awan, naik bukit, jumpa ada awan, window kereta tu basah, ataupun kita boleh rasa basah tu memenuhi kita punya muka. Kalau siapa yang naik motor ke atas bukit lah, dia boleh rasa.